Welcome back, everybody. So this is section 2.2. Now, the unique part about section 2.1 is that all of those ways of displaying data didn't really show each piece of data within it, right? And we talked about that a little bit yesterday. In a frequency table, you can't tell what the data actually are, right? You can't tell what individual entries are in that. So while a frequency table is useful, a histogram is useful, an ogive is useful. It's really just useful for seeing trends, right? Seeing trends within the data. You can't actually see specific pieces of data. So that's what we're going to talk a little bit more about today. Okay, what are some types of distributions, or what are some types of displays that you can actually see each individual piece of data? First thing that we're going to talk about is stem and leaf plot. Now, I'm going to show you a lot of these things. It might be a good idea to write down like the rules of how you create them, the rules of, just the rules of them, and maybe draw yourself a diagram of one. The homework, you actually create them, or you have to tell some things based off of them. We have our stem and leaf plot here. Stem and leaf plot. So maybe this is a set of ACT scores. This is a set of ACT scores where we have, think about stems and leaves. The stems are the tens digit and the leaves are the ones digit. It's always good to make sure that you write a key in your stem and leaf plot. Because, I don't know, maybe 1.7 could represent 1.7. Wait, that's a bad ACT score. But maybe 1.7 could represent one. If I didn't know anything about an ACT score, I didn't know what the parameters were. I mean, we can understand that it's 17. But we don't know. Maybe 1.7 is 1.7. So it's always good to write a key out. Now, the nice thing about a stem and leaf plot is that you see every piece of data. So we see that, one person scored a 17. 2 people scored an 18. 1 person scored a 16. 1 person scored a 19. Does this have to be in order? No. It could be in order, and you're going to see most of them are in order. I don't know. It just weirds me out to see them out of order. But it doesn't have to be in order. Okay. So stem and leaf plots are interesting because they're kind of like a histogram where you can see the trend of the data. It's separated by categories almost, but you can see individual entries. Like if I look at a stem and leaf plot with my head tilted to the side, it kind of looks like a histogram. Whoa, that's not a pen anymore. Right? It kind of looks like a histogram. We can still see the trend in the data, where most of my data falls in the middle there, right? This almost has like a bell-shaped curve to it, right? Most of the data falls in the middle there. So a stem and leaf plot shows you trend, but also shows you individual scores as well. Okay, they're still kind of separated by categories. So what are the categories here? It's something that falls in the tens place, something that falls in the 20s place, something that falls in the 30s place, right? That's kind of like our categories, our intervals, if you will, right? But a stem and leaf plot will not only show you trend, but also show you actual individual pieces of data, okay? Some variations on stem and leaf plots that you could possibly have. You could have not only just separated by tens, but also separated in half. Like you could do this, where you have, cut it in basically up by fives, right? Where you have, this looks like it's 20 to 25, and this looks like 25 to 30, and this looks 30 to 35, and then beyond that, there's a little more possibility beyond that, but you get the idea there. What is perfect score on an ACT? 36. 36, right? Okay, that's right. Something ahead of my head was 32. So this is one variation on a stem and leaf plot. You can categorize it a little bit differently. You can chunk it up a little bit differently. You can have, and I don't think this is on here. No, but you can have a double stem and leaf plot. So if I had said maybe I was going to compare two different classes. Maybe I was going to compare, my class against Mrs. Napolz's class, and take a look at their ACT scores. You could put another side onto this and say, well, what if I put my scores on the left side? Maybe we got a 6, a 7, an 8, and a 9, and a 21, a 22, 22, 23, 23, 24, 25, 25, 26, 31, and then we can see this. And then you can see not only trend in one set of data, you can see trend as a comparison to another set of data. I can basically see now that, well, Mrs. Napolz's scores had a higher average, probably, right? I could calculate it, but I can just visually see, yeah, there are more scores clumped together in the upper 20s, low 30s than I had. So I know her class in general did better than my class. Does that make sense? So that's called a double stem and leaf plot, where you can use the stems, but go not only to the right, but also to the left side. That's one way to do it. Just showing you here another version of a stem and leaf plot, right? Just another way to do it. You can run it all the way up through double digits, like this 149, right? Why am I showing you this one? Well, I can see based on this, 149 is an outlier, right? 149 is an outlier. I may not have been able to see that if it was just represented as a table. I might have guessed that it was an outlier, but man, it's way far down there, way far separated from a lot of our data. And I can see most of our data is chunked in the 20s and 30s. There is another chunk in the 70s to 80s, right? But 149 is an outlier. Man, somebody's texting a lot. I wonder how many text messages you send per day. Maybe that's somebody's project. Maybe somebody should do that for fun. Can you calculate that? Like, is that part of like your screen time app on your iPhones?
You just have to count it.
You just have to count it?
Probably.
Let's see.
Do you count groups? Or would you count? Yes. You count groups?
Like text messages sent.
Oh, sent, not
Sent.
not given.
Like only text messages or like all messages?
Ooh, see, now that we're getting into
Yeah, that's where it gets at.
that gets interesting. So dot plots. Okay, another way to represent data visually, where I can see all of my pieces of data, right? I can see the spread of the data now. I can see how much it varies. Right? This is just another type of visual representation. I gotta be honest, I don't use a dot plot a lot. Rather, probably use a stem and leaf plot rather than a dot plot. But it's just another way to do it. This is that same set of data for the number of text messages sent, written as a dot plot rather than a table or stem and leaf plot. Just another way to represent data. You put it on a number line. You could go by intervals. You could go by single values. Doesn't matter. Just make sure you note it on your number line. Then you just put a dot for every placeholder that you have. So it looks like there's 4 people that had probably 33. Seems like a low number. 33 text messages sent per day. I think that's a low number. So what messaging? What app would you use if you wanted to send somebody a message?
Snapchat, Instagram.
But what's your go-to?
If I don't have their number, Instagram.
Snapchat for sure.
Snapchat.
I prefer text messaging. It's easier.
Yeah, I guess it depends on who the receiver is.
Exactly.
If you texted mom,
Who I need to get a hold of.
you go to Snapchat.
I go to Snapchat.
For your mom?
Oh, not for my mom.
I go to messages.
Well, for like my mom and my dad and my grandma, it's like
Text.
text, but everyone else pretty much Snapchat. Unless I really need to get a hold of them, then I'll like send them a text.
Oh, so it's like urgency.
Yeah.
Oh, okay. So like if it's like I need an answer back, you send a text.
Yeah.
Why? Does it get there faster?
Because you can't see what someone messages you on Snapchat unless you click it. If it's a
You
text,
have
so-
I think people ignore Snapchats.
Oh, really?
yeah, if you
It's a less
text someone,
formal.
they can see it.
And you can see. Okay.
I
I
always
don't have
tell people-
Snapchat, so I don't even know.
I always tell people if they need me, I'll give them my number.
Yeah.
I won't give them my Snapchat or
Yeah,
Instagram.
yeah.
I'm never.
Because do you have to be like friends with that person to be able to message somebody on Snapchat?
Sometimes
Sometimes.
I get random Snapchats from random people I have never even added back.
Weird.
Yeah.
Interesting. A pie chart. A pie chart. One of the most common visual representations of data. Now, this is where we kind of get back into, I can't see individual pieces of data anymore. Pie charts are extremely useful to show different categories, especially in if the data set, if the response may be qualitative instead of quantitative, a pie chart might be very useful. For a qualitative set of data, you ain't doing a stem and leaf plot. You're doing a dot plot. Pie chart, however, so a pie chart is a circle that is divided into sectors that represent categories, and the frequency with it, that category is responded with is represented in the pie chart. So, for example, here, maybe this is LeBron's portfolio, where his investments are. He's got 2.5 million in real estate. That sounds like a lot. That sounds like a really big number, right? But looking at the pie chart, that's actually only just a small portion of what he's got. Looks like most of his money's in stocks. 41% of his money in stocks. $12 million in stocks. $5 million in mutual funds. $10 million in bonds, and $20 million in savings. And we can see that cut up here. Oh, savings. Oh man, I'm colorblind. That's why. That's savings. Okay. So stocks, it's only 25% of stocks. Excuse me. Okay. But you can see basically where things are spread out, how things relate to one another. I can see here that I have, twice as much money in bonds as I do in mutual funds. I can see that I have about 2 times as much money in savings, right? Savings as I do in bonds. I can see the smallest thing that I invest in is real estate, buying houses. Now, the one chart that we are going to create here today is we're going to do a pie chart together, because I think that's like one of the more difficult ones to actually make. You might have done this already. You might know this. Great. We're going to do it one more time for old time's sake. Okay, we've got this table here. We've got earned degrees conferred in 2014. I just took this from the book. I'm not sure if this is across the U.S. in number of thousands. Yeah, maybe this is in the U.S. in 2014. Yeah, that makes sense. Like 178,000 doctorate degrees in 2014. Yeah, that makes sense. So let's say across the U.S. we've got this many of each type of degree. Notice that, again, this is a qualitative response, right? So we can represent it as a pie chart. So let's first start by calculating the chunk of the pie that this is going to represent, right? Basically finding the relative frequency of these things. Let's first start by finding our n value. 1,003, 1870, 754, and 178. 1,003, 1870, 754, 17, 3805. 3805. Okay, and now we are going to add a column onto this and find the relative frequency. Okay, we're going to find the relative frequency of each of these. Remember, relative frequency is just basically the percentage that falls within that data. So I've got 1,003 divided by 3805. You take the frequency divided by n. So 0.264. Let's take 1870 divided by 3805. And that gets me 0.491. Let's take 754 divided by 3805. It's going to be 0.198. That's a 9. Remember that. And then 178 divided by 3805. 0.047. So that's the percentage. You know, if I'm making a key, if I'm making a table along with my pie chart, I would put those percentages along with it. 26.4% is going to be associate's degree. 49.1% is going to be bachelor's degree. 19.8% is going to be master's degree. And 4.7% is going to be our doctorate degree. Now, how does that relate to our pie chart? Well, the best way to do these things, if you're doing it by hand, if you're doing it like actually sketching the graph, the best thing to do is find the degrees that you would need here. Like, for example, 0.264, I would take 0.264, that's 624, 0.264 of my total amount of degrees, 360 degrees. So I know this is 95, add another column on here. To create that chunk of the pie, I would take a protractor and use 95.04 degrees. So roughly 95 degrees. Go to the nearest degree. 0.491 times 360 would get me 177 degrees. And again, you're kind of ballparking here. Round it to the nearest degree. 0.198 times 360 is going to get me 71 degrees. And then our doctorate, 0.047 times 360. Smallest chunk that we have is only 17 degrees. You know, I may get a hair over 360 degrees. I wonder what I get. 95 plus 177 plus 71 plus 17. Oh, wow. That was really good. My rounding was awesome. Came out right at 360 degrees. But if you're one over or one under, you know, it's okay. Just don't make it like, you know, you should be at like 380 degrees. That something went wrong. Okay, so I'm going to make myself a circle here. And then I'm going to say, well, start with my biggest chunk. My biggest chunk is bachelor's degree. It's 3 degrees less than a half circle, right? So I'm going to say 3 degrees less than a half circle. I'll go straight out to the right, just a hair underneath a half circle. So that is my bachelor's. So we can say bachelor's here at 49.1%. And then we could say, well, 95%. So 95 plus 177. Okay, so that's going to get us just a little bit more than 3/4 down below, right? So maybe just a little bit down here and say, okay, so that is going to be bachelor's. Oh, no, excuse me, associates. And that's 26.4%. 71 degrees. Okay, just gotta kind of ballpark that. 71 degrees. So if this is 90, so let's go 70 degrees somewhere down here. If I'm being exact, I should get a protractor out and actually use that. But for our purposes up here, this is just fine. Masters, and that's 19.8%. And then in here, we'll just put an arrow in. That is doctoral degrees at 4.7%. That makes sense? That's how to properly construct a pie chart. properly constructed pie chart. Could you have done this based on the percentages alone? Yeah, I mean, 49% of a circle is just a little less than half. Just a little less than half. A semicircle. 26.4% of a circle. Okay, that's a little bit more than a quarter of the circle. You can kind of ballpark it on that, but to get really formal about it, you should take the degrees. Should find the degrees. Okay, pie chart. Next thing we have is what's called a Pareto chart. A Pareto chart, probably one of the least well-known charts. Basically, it's like a histogram for qualitative data. It's like a histogram for qualitative data. Used for qualitative data. Bar graph in which the bars are positioned in decreasing height. That's like one of the only stipulations for a Pareto chart. A Pareto chart goes in decreasing order. Because what other order are you going to put it in, right? It's not going to be like any sort of value, right? You're not going to put it, because for a Pareto chart, if it's truly qualitative, I guess maybe alphabetical, maybe that would be, but it would make most sense to put it in decreasing order in terms of its height, in terms of its frequency that those things were responding with. So I've got two Pareto charts here for you. The bars can be touching, but they don't have to be touching. It's not like we need boundaries here, right? It's not like something's going to fall between a category. No. GM, Ford, Toyota, Honda, or Chrysler makes of cars among seniors. What? There's no. Nobody has a Porsche out here. Oh, that's me. That's my car. That's right. Yeah. Top 5 causes of death in the United States. Notice again, decreasing order. Goes in decreasing order. Always make a scale along the y-axis. The scale along the y-axis is always the frequency, and then along the x-axis is your qualitative categories. And that is a Pareto chart. Pretty simple there. And then second to last type that we have is a paired data set, which is a scatter plot. A paired data set. And yes, we will actually, I know probably most of you have done a linear regression from this point. If you've taken Algebra 2, you've probably done a linear regression. We will actually do that in chapter 9. We will do a linear regression. But we get to do it by hand. We can use our calculators. Yeah. So much fun. Yeah, using finding a line of best fit, finding the equation of the line of best fit. We'll do that by hand. Awesome. No, it's very fun. But a paired data set is when each entry in one data set corresponds to one entry in another data set. A scatter plot are ordered pairs that are graphed in a coordinate plane. We've done a lot of scatter plots in our math lives. But it's used to see trend. The trend that we see may be linear. It may not be linear. It may be quadratic. It may be exponential. It may be logarithmic. There's a lot of different ways that you could represent data. These are just two. Pulled the second one out of the book. This first one here is just velocity versus miles per gallon. We actually see that as you increase velocity, as you increase speed, your car runs more efficiently. That's why when you travel on the highway, you actually get more miles per gallon because it's running more efficiently on the highway rather than just stop and go traffic. But there is a breaking point. There is an optimal speed. You can optimize this, which we will do in calculus. You can optimize that and say, okay, what is the optimum speed to get your what speed do you have to go to optimize your miles per gallon? Fisher's iris data set. What is that? Petal length? Oh, it's like not iris in terms of eye, in terms of flower. I was like, what are you talking about? Iris. Like the flower. Iris flower. So petal length as it corresponds to petal width. So flowers' petal lengths as it corresponds to their petal width, and we would imagine that as I increase the length of the flower petal, the width would probably increase as well, and that's what we see here with the trend in that data. As I increase petal length, looks like petal width is increasing as well. Okay. But again, you can see trend as it corresponds. You can see correlation. You can see how one data set is corresponding with another data set. You can see if there is a relationship and test that relationship. And then the last thing that we have is a time series chart. A time series chart. You would call this a line graph. Yeah. What calls it a time series chart with respect specifically to time. A time graph. We'll call it a time series. A data set that is composed of quantitative entries taken at regular intervals over a period of time is called a time series chart. Time series. So if we calculate the average daily temperature and we graph that, regular intervals every day, graph it, make a time series chart. This is motor vehicle thefts in years. Okay, forget about the burglaries here. But this is motor vehicle thefts in years. Looks like from 2005 to 2015, it decreased steadily. We could compare that. You know, I wish I had the diagram here, but you could do a double time series, right? Where you can put two line graphs, two time series charts on the same graph. You know, if I graph this 2005, 26, 2.16, so it's way up here. Okay. 2.19. I would butcher that. But you could put two time series charts on the same one to see, okay, are things trending together? Are things going up at the same rate? Are things going down at the same rate? Is something decreasing faster than something else? Is something increasing faster than something else? Another example here, the population of Seattle by year. Just another version of a time series chart. Another version of a time series chart. All right, that's it for today, my friends. Let me turn off the video.